Okay, this is our second example. We want to find a tension in a beam, tension in a cable, actually, tension in a cable that supports the beam. So here is a beam. Uh, so this beam has is supported at a pin which it can rotate. If it was just the pin, then it's kind of like an arm. So you can think of this arm. The pin is here, and the arm is can go like that. So this is just some support, and then it will rotate, right? If nothing was supporting it because of the weight is acting on it. So there's a center of this is that's where the weight is acting, and so it will not weight will be balanced by some kind of normal force here, right? So the um, it will not go down like this, but it will rotate as such, right? Um, to to balance this, there is a there is a there is a cable that's holding it, and so if you look at the the force on the cable, force on the beam by the cable is that way. So there's a tension like that, and there's a weight that way, and then there's a we can say normal force uh, from here is in some direction which is balancing all of these. Okay, so force by the pin on the bar has to balance both this and that. So this is mg, and this is tension, and so this is angle theta. So if these were the only forces on the beam, this cannot cancel that, so the beam will accelerate. So there must be some force here, right? So if you just draw a force diagram, you have mg that way, tension that way. So that's the situation right now with these two forces. So if you add these guys, you are going to get a force that way. So this is the force has to be balanced by the pin. So the pin force by pin must be in some direction, which we don't know yet. We can find it. So normally the force by pin, we address it by its x and y components. If this is the x direction and this is the y direction, the pin will have some x components, some y components, so some fx, some fy. So we say the pin is pushing on it some fx and some fy. So pin is kind of, so what you used to call normal, it's going to be this way. When we had a box on a plane, then normal was just that way. It was not this way. Here the normal is actually a combination of these two guys. Okay, so we have if you look at it, we have we don't know the value of this force. We don't know how much tension there is, how much fx there is, how much fy there is. What's given to us, a mass, and also given the length of this thing, length of the of beam, and angle theta. So these things are given, and fx, fy, and t are not known. Fx, fy, and t not known. Since the beam is going nowhere, right? I mean, it's being supported, so there is all the torques will cancel out. Net torque will be zero. Net force is zero because there's no acceleration. So in this situation, if we not interested in fx and fy, just tension, then a torque balancing equation about this point is very useful. So we're gonna say balance, workout balance of torques about O. So why did I pick O? Why not about that point or some other point? I picked O because I don't need to know fx and fy, right? We don't need to know fx and y. So if I pick O, the torque by fx will be 0 and torque by fy will be 0 because the lever arms will 0. This will have the added benefit. This is a benefit to our calculation, that torque by fx equal to 0 and torque by fy equal to 0. And that's because this is 0 because their lever arm about O is 0, R0, right? About 0. So all I have to do is figure out the torque of this guy and figure out the torque of weight. Now weight always acts at half the at the center of gravity, or center of the object. If object has some kind of symmetry, it's going to be at the center. So this distance we know is L over 2. Okay. So I need to figure out the torque of this guy and torque of this guy, and see if they are the opposite direction. If the opposite is, this will subtract, and so their subtraction will cancel out, right? Set equal to 0. So it will have only one unknown. Let me erase and make sure we can understand how the torque calculation will go, right? So this is all set up. So now we can actually find the equation that will help us solve what's the tension, right? So the tension, the torque by mg, let's talk about torque by mg. So torque about O, so the axis is coming out, about O of mg. So this will simply be, I'll go through the same process, right? So I have bar, I have this, and mg. So remember, recall that recall that you have certain number of steps you follow when you use lever arms. So one of the steps is to make this like that. So this is, what is it called? Do you remember that? It's called line of force. So you just make a line of force, and then from this pivot that you selected, you draw a perpendicular to this line. Not just any line, you draw this, and this is 90 degrees. That distance will be the lever arm of this force, and that's just this is our lever arm of mg, and I take mg and multiply with that. So this I get, and this is equal to, in this diagram, is L over 2. So this is mg L over 2. But we're not done. We have to say which is a clockwise or counterclockwise sense. This is very important, right? So when I ask myself, if I'm not rotating right now, right? This is not rotating anything. If this was the only force, that's the important question. If this was the only force and the axis was here, which way this bar will rotate? Well, it's going to rotate like that. So it's going to be what? Clockwise or counterclockwise? Yep, clockwise. And some people like to put a minus sign here to indicate clockwise. All right, but I like to kind of visually see it. That helps me. Okay, so we got done with one of these. I need to do tension, so I do exactly the same process. So I have a bar here, and I have the pivot here, and the force is that way. So those are the things I got. So step one is, do you remember step one? Step one is going to be, I think you should know this step one by now. Step one is just make this line long, right? Step two is going to be from go here and not just draw any line here, but draw a particular line that hits that line at 90 degrees so that you get a right angle triangle here going. Remember, this is theta, which is known. That theta is known for us. Originally we said this is known, and n and g and l are known. Those are known quantities. Okay, so I need to figure out, this is the R perp for the tension force. For the tension force, that's the lever arm. Well, what I have is to figure that out. This distance is L, and this opposite. So our perp tension force is L. What do you think it's going to be? L sine theta, right? L sine theta. This is 90 degree triangle, but it's a little bit, you know, it's in a kind of weird way. I have to imagine this is 90 degrees. You may remember this shape kind of formula, but you have to kind of think adjacent, and so if this is angle theta, then that's the opposite, right? And this is the adjacent, and this is the opposite, and that's what the case over there is. Okay, so what do I have? Torque by a torque of tension about O, so same thing, is equal to, I take this and multiply by the magnitude, and that's what is unknown. Unknown is this T. So T times this, L sine theta. Am I done? What do you think? Am I done? No, I'm not done, because this just gave me the magnitude. I need to know the sense. So what do I do to figure out the sense of rotation of that? Well, I go here or here, and I ask, the tension is that way. If that was the only force that was acting on the beam, which is kind of weird. It's not the only force, but we have to pretend it's the only force. Then which way it would have rotated? Well, it's rotated counterclockwise. So this is counterclockwise. And sure enough, they're in the opposite direction. So they have a fighting chance of cancelling. And there are no other thing that have torque. This has zero torque, this has zero torque. So there were four forces, so to say. There were one force, two force, three force, four forces. But about O, only these guys have non-zero torque. So we use net torque. Tau net is 0 here. That means if I call this guy plus, then this is minus. So I have a TL sine theta from here plus minus MGL over 2. So we've got these two, one contribution, I've considered that plus, then plus. This then, because of clockwise, this is going to be a minus. I add all of this, and that's equal to 0. Okay, so when I solve this, I get T equals to mg over 2 sine theta. If I had a numerical value, I'll at this point put the numerical value. Say m was 100 kilogram, and say theta was 30 degrees. Then I put it over here and say g is 10 meter per second square. So I'll get T is equal to 100 times 100, 100 times 100, and 2 times half. So that's a, I'm sorry, 100 times 10, not 2. So 1000 Newton. That will be the answer if I had numerical values. But there's as long as you can keep track of which symbols you know, and which symbols are given and which symbols need to be determined, I think it's better to work with just symbolically here. All right. Try practicing symbolically before, you know, just before putting numbers in. I'll do more examples. I'll see how this video turned out.